Welcome back to Probability and Statistics 1. We are discussing our first major example in the course, this color sequence process with replacement. And in the last video we defined the process. We'd like to start looking at some of the random variables associated with the process and the properties of those random variables. But to do that, first we need to answer a question we raised in the first video on the color sequence, which is how to calculate the probability of a particular color sequence. And if you work through the discussion questions in the last set, this theorem will come as no surprise to you. If you have a specific color sequence, which I'm denoting here by I, so that's going to be a sequence of zeros and ones of length n. I'm just calling I1 the first element of that sequence, I2 the second element, and so on. If that's a fixed color sequence of length n, then the probability that that sequence occurs is actually expressed in terms of the success probability as follows. It's the success probability raised to the power of the number of red balls in that sequence, so that would just be the number of ones in the color sequence, times the failure probability, 1 minus p, raised to the power of the number of green balls in the sequence, which of course would be just n minus the number of red balls in the sequence. So that is simply a result of the fact that each red ball is drawn with probability p, and each green ball is drawn with probability 1 minus p. And because of the way of the counting is done, as we saw in the last set of slides when we worked through that example, you'll wind up with p multiplied by itself n sub n times, where n sub n is the number of red balls, and 1 minus p multiplied by itself n minus n sub n times, which is, or in other words, the number of times that a green ball appears. That theorem is going to be fundamental to us going forward, because it will enable us to calculate probabilities associated with all these random variables associated with the process. So just a few remarks on that. First of all, n sub n of I represents the number of ones, or the number of red balls in the sequence of length n. So n minus that would be the number of zeros, or green balls, in the color sequence. Importantly, we can also express n sub n, the number of red balls, as a sum of the indicator variables, right? Because remember, an indicator variable is 0 if the ball is green, 1 if the ball is red. So if I just sum up the indicator variables for trials 1 through n, I'll just get the total number of red balls that were drawn in that sequence of trials. So n sub n is just the sum from k equal 1 to n of I sub k. And this shows that n sub n can be thought of as a function on the sample space, right? Because the I sub k's, we already know, are functions on the sample space. So that means that n sub n, the number of red balls that are drawn, is also a random variable. So we're going to be basically studying a number of random variables associated with this process. And just to list a few of them, of course, we've already talked about the indicator variables. We've now introduced this n sub n, which is the number of red balls drawn in trials 1 through n. But you could also think of a host of other random variables. The trial number of when the jth red ball is drawn. For instance, when would the 5th red ball be drawn? Does that occur on trial 5, or maybe 6, or 12? And you could ask that for what's the trial number of the 100th red ball drawn? That's called T sub j. T sub j is the trial number of the jth red ball that appears. And then this difference between adjacent T sub j's, which I'm calling delta j, right? Like if the 6th red ball appears on trial 12 and the 5th red ball appeared on trial 9, then the number of trials between the 5th and 6th would be 12 minus 9, or 3, and that would be called the inter-arrival time. So the time between adjacent red balls is what this delta j. The delta j is the number of trials between the jth red ball and the next red ball. This by no means is all the random variables you could think about associated with this process, and you should try to think of some. What are some other random variables associated with this process? And there's literally an infinite number of them. Just think about sort of any question you could ask about the color sequence property process. Any question you could ask that's confined solely to the notion of, well, what was the color sequence, right? Uh, the answer to that question would be a random variable, right? So, like, think about some questions you could ask about the color sequence, and see if you can use those questions to define some more random variables on the process. Let's take a quick look at the indicator random variables, the I sub k's, because they're sort of bedrock. They basically give you all the information about the process, right? On each trial, was the ball drawn red or was it green? And we know that this is coded by the I sub k's. I sub k is 1 if the kth ball is red, 0 otherwise. And from that, we can easily get the distribution, the probability mass function for the I sub k's. The probability that I sub k is 1 is just the probability of drawing a red ball, which you already know is that success probability, P, R over R plus G. And the probability that I sub k is 0 is the probability that a green ball was drawn, so that's just 1 minus P. And so those are the only two possible values, and so we have its distribution. This random variable, these indicators, are known in the probability literature as Bernoulli random variables, and the distribution that you see here is called the Bernoulli distribution with success parameter P. It's basically one of the simplest distributions you can think of, right? It has possible values 0 and 1. The probability of a 1 is this number P, and the probability of a 0 is, of course, 1 minus P. And theorem 3.10 elucidates some of the main properties of these Bernoulli random variables in terms of their expected values and their variance. And so the expected value of any of these I sub k's turns out to be just the success probability P. The expected value of the square of any of these random variables is also P. We're going to need to know the expected value of the product of two different indicator variables. So the expected value of ik times ij, where k is different than j, that turns out to be p squared. And then from that, we're going to be able to find that the variance of I sub k is p times 1 minus p. So the variance is the product of the success and the failure probabilities. And these all follow from just basic properties of the color sequence process and properties of expected value that we've already seen. So for instance, to find the expected value of I sub k, you just take the possible values of I sub k and multiply them by the probabilities that those values actually occur. So that's what you see in the first line there. And then, of course, we know the probability that I sub k is 0 is 1 minus p, and the probability that I sub k is 1 is p. So we get 0 times 1 minus p plus 1 times p, or just p. So the expected value of I sub k is just p. And that kind of makes sense. I sub k is telling you when, it's 1 if the ball drawn was red, and that happens with probability p, so it's not surprising to see that the expected value of I sub k is just p. Notice too that this is true for all the I sub k's. The expected value of I1 is p, the expected value of I2 is p, and so on. The expected value of I squared can be computed in the same way, and here we're using a theorem about computing the expected value of a function of random variables. So it would be possible values of I squared times the probabilities that those values occur. So you have 0 squared times the probability of 0, plus 1 squared times the probability of 1. And if you work that out, you again get the same result, P. And from that, you can find that the variance of I sub k is P times 1 minus P. And we're using here, in this little derivation, we're just using the fact that the variance of any random variable, the alternate formula for it is that it's the expected value of the square minus the square of the expected value. So we just calculated the expected value of the square as P. The expected value of ik is also p, so when we square that, we get p squared. So you have p minus p squared, or p times 1 minus p. So a few discussion questions here. Let G sub n be the number of green balls drawn in trials 1 through n. Can you express G sub n in terms of the n sub n variables that we've already discussed? Can you express G sub n in terms of the indicator variables, I sub k? You can, and you should think those through and come up with formulas for G sub n in terms of either n sub n or the I sub k's. Second bullet point proposes a little game in which I pay you $1 for each red ball that's drawn, but you pay me $1 for each green ball that's drawn. Can you express the total amount of money that you pay me in terms of these variables n sub n, or G sub n, or the I sub k's? The answer is yes, you can, and so think that through and find out how you can express the amount of money you pay me in terms of these variables. We'll leave it here for now. When we come back, we'll actually look more deeply into the random variables n sub n, which are called binomial random variables. They give the total number of successes in trials 1 through n, and they're very important in probability theory. So we'll be looking at that next. In the meantime, y'all take care, and I will be back at you real soon.